We'll wait for a few more minutes for the students to join.
Yeah, sure. I just send a reminder to them.
It seems not many students attend now, is it? Are they busy?
It's like, I think, vacation time, and then the exams are getting closer, so lots of assignments due, etc.
I see.
So,
Okay.
coming down. I think if we do something similar later, I think the summer would probably be a good time, and they would have much less load.
Okay.
Or early in the semester, both of these should work fine. I think people are joining in. That's good. We have about 11 students, so maybe
okay.
Get started.
Okay, I think we might start then.
Sure.
Okay. Good afternoon, everybody.
You join in using a browser or the app today?
Oh, I use the browser. In fact, I copied to the browser and then.
Okay, I see. Like last time.
That's what last week I was stuck up, so I thought I'll go this way. What
right. Which worked.
Okay. Okay, now today I would continue with my previous lecture, which was on the notch. Screen share. Share. Okay, so can you all see my presentation on the screen?
Yes, we can. Please go ahead.
Now, before I go further, are there any questions from the previous lecture, which was the hole damage in the laminate? And we talked about mainly the point test criteria. And we said it's a two-parametric semi-empirical or empirical approach. We have to determine by testing a few coupons the unknown strength and testing a couple of hole diameters, determine the correctest dimension, and consider the effect of the layups and diameters in order to properly account for the effect of these parameters on the characteristic dimension. Because if you use only one dimension of characteristic dimension based on, say, quarter-inch hole, and for larger hole, it might be conservative sometimes. So normal practice is to calibrate the characteristic dimension for various laminates, layups, and diameters, and plot the chart in order to cover your design space. So in summary, that is the thing about pointer stress criteria, which normally I like to use in a simple type of loading. Even in the complex loading, finally, I'll tell you that is the pointer stress criteria is useful, even if you are having multi-axial loading cases. So now similar analysis we will carry out for the notches, like the sharp cracks in the laminate using the pointer stress. And another approach is the Marlin approach, which is very common. So based on this, again, are there any questions? Or I continue? Okay, so we'll be discussing now the sharp notches rather than the holes now. And the approach for the notches is also similar to what we discussed for the holes based on the pointer stress criteria. So what you see on the screen now, a crack of 2C dimension, or the length 2C. And on the right of this, I show a pictorial representation of the stress near the notch tip varying from the notch tip to away from the notch tip. And as you can see from this, right near the notch tip, the stress, theoretically, it goes to infinity because it's a stress singularity at the notch tip. That is theoretical singularity, but the stress can never reach infinity. The reason being, you will have in metals, you will have a plasticity developed near the crack tip, which will restrict the stress reaching to infinity, because yielding will occur and the sigma y will be the yield stress will be the maximum stress normally if the material yields. Similarly, in composites, you will find this stress right over here will cause some kind of a damage zone, similar to what we saw for the holes, a small damage zone, which will try to reduce the stress near the tip. So using this damage zone concept, the pointer stress criteria was developed, as I said last time. And it's no different to the hole. The criteria definition is saying that the failure would occur when the stress sigma y at the characteristic dimension, right at this point, is equal to the unnotched failure stress, which is sigma naught. So in terms of mathematical equation, the criteria is written as sigma y at x equal to c plus d1 at y equal to 0 is equal to sigma naught, which is unnotched strength. So this is the pointer stress criteria, a simple criteria. And D1 is pointer stress characteristic dimension. Okay, now writing this stress expression The stress distribution for the crack is far simpler than the hole. You can see this equation, you can always remember sigma y upon sigma g, which is the gross stress, is equal to x upon under root x square minus c square. And this term basically gives the stress singularity, under root singularity, which in metal fracture mechanics we talk of, under root singularity. Substituting equation 1 into equation 2 leads to this, juggling with the equation. I have written this sigma n infinity, which denotes that for infinite plate, in larger plate, for a particular crack size of C, semi-crack length C, is equal to 1 minus eta square, and eta is defined by C upon C plus D now 1. So this expression for the notch is far simpler to the point stress criteria for the hole, where you won't remember the equation easily, and this one you can remember easily the equation. Okay, so that means in order to determine this strength, what we need, sigma naught, similar to the hole, and D1, because C is known, D1, which is characteristic dimension. So it's a two-parametric approach again, similar to the hole. Okay, now, normally what will happen in the structure, you don't have the infinite plate, that is the crack, is small enough compared to the size of the plate. So you have to apply a finite boundary correction factor, and we call that configuration factor or finite width correction factor. Say I've written as a Y3, just to differentiate between the other configuration factors for the whole. Yeah. So Y3 is under root sec pi C by W. You may find in fracture mechanics books several different expressions for this finite width correction factor. If you pick up the Bro-Eichlin elastic fracture mechanics, you can find the sec term and then equation polynomial type also. So there are many expressions given, but they are all okay. So this is a finite boundary correction, finite width correction factor. Now, for a very large crack, when C is much larger than D1, then the equation which was there for eta, so this one, what can happen, if C is very large compared to D1, you can ignore D1 and this becomes 1. Of course, that becomes then 0, which is not possible, sorry. So equation 4, in fact, you have to use the inequality and then 2d1 upon c. You have to use this equation in order to determine the effect. When d1 is small, you can ignore this. Okay, now so sigma n upon sigma naught, 1 upon y3, and 2d1 by c. So this is for large crack. Anyway, normally we don't use this equation. Okay, determination of characteristic distance. This is similar to the whole problem where you would test a couple of coupons with the different notch sizes. You can do it in tension, you can do it in compression because the behavior in compression and tension will be different. And so you will need to determine the parameters for compression and parameters for tension. So test different notch lengths, different layups, similar to what I said for the house. And then you can determine these parameters with the layup, thickness, notch size, the material, because it's all dependent on many parameters like layup, material, and notch size, thickness. Okay, so hey, schematically I've shown some plots over here. That's what you might have to do for the covering the design space. So characteristic dimension D1 may vary with hole size, layups, and loading, tension, or compression. It may therefore be necessary to develop the charts for D1 variations with layup and hole size for tension and compression. Okay, now some test data comparisons. This I have taken from the original paper by Whitney and Usman data for tension, coupons, and as you can see, there are two different types of coupons, 090 and 045 minus 45, 90, which is quasi-isotropic. And you can see here, red one for quasi-isotropic and blue ones for 090. And fitting the curve for different characteristic dimensions, as you can see, for D1 1.5, this fits over here, but over here it starts deviating. So it seems to me as the crack length increases, you might have to use different characteristic dimension because it seems the same characteristic dimension doesn't fit the data set. And this is what has to be always done when you have a large number of data sets available. You can generate the equations for the characteristic dimension variations with the crack length and layups, as I said. So there are always variations. Just schematically, again, I plotted here the effect of characteristic dimension on the strength. As we understand, as the characteristic dimension goes up, the strength also goes up. So a smaller the characteristic dimension, lower the strength. And you can see the amount of error you can generate if you don't choose the proper characteristic dimension. You can see, suppose the crack is 5 millimeter, that means 2C full crack length is to 10 millimeters. If you choose this one, you will get about say 0.5 ratio. And if you choose this 1 millimeter, you will be able to achieve almost like a 10% higher strength. So characteristic dimension prediction accurately is important rather than choosing just a conservative value and say, okay, if you choose very small one, we can be conservative and the failure would not occur, margins may lower. However, the downside of that is that you may drive the weight of the structure unnecessarily higher. So conservatives when needed, but not to a great extent in aircraft industry. So, and that is why in aircraft industry, there's a big emphasis always to develop the allowables, which are good allowables, covering all your design space, so that you are neither conservative nor optimistic too much. It should be the realistic data validated by test always. We in industry never accepted anything without validating by test. And that's very important thing in the industry, aerospace industry. Everything has to be validated. Okay, now comments on the point distress criteria. In fact, I have commented most of it, but I'll just read out here. So it's a two-parametric empirical approach, whether it's a hole or a crack. Strength predictions depend upon characteristic dimension, D0 or D1, accurately. The characteristic dimension is seen to depend upon layup, type of material, layup, thickness, notch or hole size, and the environment. Pointer stress criteria useful for fiber dominant layups and a poor prediction for the matrix dominant layup because of failure mode change. So it's not very good. Like I suppose you have a 80% 45 and 10% 0. That's where using the pointer stress criteria is not very good. Yeah, you will have to if you want to use it, of course, you will calibrate the correct dimension for a particular layup and use it. In compression, generally matrix dominant layups show lower strength than predicted based on the stress concentration. It seems the strength in such case may be controlled by mechanisms rather than fiber. So our experience has been sometimes the compression strength may be lower than even the stress concentration factor for the whole. So again, it has to be validated by the test properly. Okay, Marlin approach to parametric approach. Now we discussed so far about the pointer stress criteria, but there's another approach which is very commonly used instead of pointer stress. The approach given by Professor Marr and Lin. Lin was a student at the MIT people long back. So what this criteria defines, we'll discuss here. We know for an isotropic material, the classical linear elastic fracture mechanics provides the notch strength as defined by sigma n, that is notch strength equal to 1 upon y3, the configuration factor K1C, which is the fracture toughness of the material, divided by root pi c. This is standard equation from the linear elastic fracture mechanics for isotropic material. Where stress singularity, what you see, root pi c, and that's what we call the root singularity. This is under root or 1/2 singularity. Now, this is common for the metal, but using the similarity of this with the composites, that's what Marr and Lin did. They said, okay, in composites, because of the damage near the zone, near the crack tip, the singularity may not remain as under root singularity, this root singularity. The singularity may be lower than that. So they propose the criteria as for composites that the strength can be governed by sigma n is equal to 1 upon y3. This is a configuration factor. We don't worry about it. It's a finite viscosity. Hc, the term similar to this Kc, they are defining Hc divided by 2Cn instead of pi, because pi doesn't make sense. Important parameter is C, of course. So they use this, and instead of that under root here, that is 1 upon 2 singularity, they put a parameter n, which is different to 1/2. And the parameters are where Hc is the composite fracture toughness equivalent to metallic fracture toughness K1C. N is the order of singularity at the tip of the crack, which is lower than 1/2. And so N is a function of the ratio of fiber and matrix shear moduli and the Poisson's ratio for different materials, in fact. And same thing, Sc. Sc is also a function of the material layup, thickness, various parameters like a correctness dimension. So there are two parameters now, which you have to determine, Hc and N. Similar? to point stress, where we had two parameters, where two parameters were characteristic dimension D and the unknotched strength sigma naught. So that means, because these are all empirical, we have to validate. There's nothing, no theory behind it. You can't determine this N and SC by theory. That means you have to determine by test, similar to point stress. So that means you have to test the coupons in order to determine these parameters. Test. For common layups, the order of singularity N varies between 0.1 and 0.5. Okay, now what's the procedure to determine it? Similar to the point stress criteria, you have to test various coupons. Now, in order to determine these two parameters, SC and N, you have to consider at least two crack lengths to calculate these two parameters. In point stress criteria, you have to test only one crack length in order to determine D1, because the other coupon is unknotched strength where the crack length is 0. Here, you have to consider two crack lengths, 2C1, maybe one coupon of 5 millimeter crack and then another one 10 millimeter crack, in order to get these two parameters calculated. Two unknowns, so you need two equations. I've written down here, basically just juggling with the equation for two crack lengths, suppose C1 and C2, and wrote sigma n on sigma n2, defined some parameter. I won't go into the details. Finally, to determine those parameters, I've written the equation here. Say n is equal to this, where A1 is defined by C2 upon C1, C2 upon C1, and A2 is defined by this configuration parameters for two crack lengths. So A1 and A2 are defined. And based on that, you will calculate from the test data, because when you have tested the coupon, you know sigma n1, that is notched strength for crack and crack C1, and sigma n2 for crack length of C2. So those two parameters are known. Based on that, you can solve these equations for the determination of N and SC. Okay, so that means you can determine N and SC based on two crack lengths. I've written just over here. So if the test data is available for various crack lengths, the best estimates of a suppose you have many crack lengths available, it's good. That means you can optimize the line equation, and then these parameters N and SC can be determined by the plot. Equation can be written over here, and suppose you have many data points, you can have the best fit curve. So we call that best fit N and HC parameters. So when you are trying to develop the method, parametric study you have to do, you will test normally a couple of different lengths of coupons to determine the best value of HC and N, calibrated over various lengths. And that will provide a better estimate than point stress criteria over the various lengths. And of course, point stress criteria also would give the same thing if you can calibrate the characteristic dimension over various crack lengths. Then there's no difference. Okay, so determination of ML parameters, I've already described it. I won't read here. It's very obvious. What I did, I picked up some test data and used both these methods, point stress criteria and Marlin approach, and try to use the best fit for both these methods. And I plotted over here. So you can see the variation of the strength. The test data is there with the red. And then the calculated values. Now, since this is an empirical method, you'd always predict the data which will match the test data well. Because what I did, I determined the best fit values for HC and N using this test data, and then calibrated those parameters, and then got it. Now, what you find here, of course, point distance criteria and Marlin approach in this region both show pretty good correlation. But as the crack length grows, the point distance criteria is slightly conservative. Marlin approach provides better fit, but for the small crack length, the trend is other way. This goes up. Here also basically, sorry. So Marlin is providing higher value, yes, and point distance criteria providing lower value, sorry. Yes. So the trend is different. And over here is different because Marlin is providing better estimate, sorry, higher value, and point distance criteria provides lower value. Anyway, this is only how these parameters get adjusted, the difference. But normally what happens for large cracks, when we are doing analysis for the panels with large cracks, we are in this region almost. Suppose you are analyzing fuselage structure, where you have to analyze the crack length of almost like a 500 millimeter. It's pretty long. So you have to validate these methods for such long crack lengths. Okay, next one. I've just written, in fact, most of the time I've been talking about parameters affecting the notch strength. Anyway, I'll just read out what is there. Notch strength is affected by several parameters like notch or hole, damage size, fiber type, fiber diameter, reinforcement types, uniform, whether it's a UD fiber, woven fabric, knitted, all these material, basically material dependent. Matrix, brittle, toughened, or thermoplastic, modulus and toughness, layups and layup sequences, laminate thickness, fiber matrix interface strength, material processing condition, material defects, porosity, voids, loading mode, tension, compression, shear, bending, hole quality, panel size, and boundary condition, environment, proximity of other damage. So many parameters affect these strengths. And you have to consider the best choice of this parameter and see if any of these parameters. Some of the parameters may not be very significantly affecting. And normally what happens, some of the parameters you have already accounted for when we are making the coupon, because we are using the same material which is being used in the design. The process to make the coupon will be the same exactly. So some of these parameters anyway will be taken care of. It's only the design parameters like a thickness, layup additions, and the notch lengths, which you may have to consider. Okay, comments on the analysis method. Prediction of notch distance are empirical and rely on the characteristic parameters such as characteristic distance for point distance, HC, and N for my ML approach. Characteristic parameters depend on laminate type material. We have talked about it. Therefore, characteristic parameters need to be established over a range of test parameters. I've already talked about it. Anyway. Now, suppose you have, instead of through thickness cracks, there are situations where you might have a cuts, gouges, and how do you determine or validate this? It all depends how much is the notch, say depth, this is scratch or gouge, and the length. So depending upon, suppose this is pretty deep, almost like a 40-50% of thickness, you would consider the damage, even though it's not a through thickness crack, you will idealize it with a through thickness crack and idealize with a through thickness crack. If it's only say one layer out of 8 layers, which is damaged, you may consider, okay, what I can do effectively, if I have to determine the residual strength for one scratch or 1 ply or 2 ply deep only, you may do the analysis using that, okay, by 1 or 2 plies are ineffective. They don't carry any load. So you reanalyze the laminate. Suppose you have an 8-ply laminate and 2 plies are damaged like this ones, you will consider, okay, I can analyze with 6 plies only and see whether the residual strength is meeting my design criteria or not. Otherwise, you might have to repair, replace the layer, and put up a scarf patch. Same thing is a continuation of that, so I won't read or do anything. Edge notches, suppose you have a notch. Again, the method is no different to what I presented. The only thing is a configuration parameter changes, only this one. Other parameters, like what we have discussed exactly, again, one won't go to. So you can have a different type of boundary conditions and different parameters, configuration parameters. These are all taken from the fracture mechanics books and many references, even the stress intensity handbook by Rook and Cartwright or Broix or any other fracture mechanics book will give you. Okay, now here the analysis methods recommendations for the hole notches based on the discussion which I provided. The holes, normally what happens, if the hole size is less than 40 millimeter, as I showed last time, that for the smaller holes, you need to use the point stress criteria, but if the holes are larger, then point stress will give you the same thing as the stress concentration approach. So unnecessarily, you don't want to create the complications. If the hole size is large, like 2 inches or 3 inches, you don't have to really use the point stress. What you can do, use the stress concentration factor approach, straight away, 1 upon kT, which will give you the same result. Simple. Okay, now, if you have notch size, of course, any size, doesn't matter whether it's a 2 millimeter crack or 100 millimeter crack, the method is same, using point stress or Marlin approach. Any questions so far? No? Okay.
Excuse me, sir.
Yes. Sure.
Sir, Pradeep, sir. Actually, you said that the failure can be predicted using stress concentration approach. What is that, sir? Stress concentration?
Oh, stress concentration. Okay, stress. Let me go back to my previous slides. You know, I showed last time this notch sensitivity criteria. Say the first one, what happens if the material yields over here when you apply the load, this section of the panel or plate. So like in aluminum, suppose material, very yielding material, ductile material. So general yielding will occur. The stresses, you don't have much of the stress concentration over here. So this is notch insensitive, we call net section through strength is given by sigma n by sigma naught equal to 1 minus d naught. That is net section failure, general yielding criteria, which you can see in metals, aluminum, suppose very ductile material. Then I said, okay, highly notch sensitive, where you have the stress distribution, where this stress is, suppose it's isotropic or quasi-isotropic, 3 sigma. So we can consider the failure occurring by this criteria, sigma n upon sigma naught equal to 1 upon y. Don't worry about this. This is a configuration factor, 1 upon kT. Okay. And then point stress criteria. And then I showed a graph here comparing all these 3 criteria, where I showed, okay, the first one, which is notch insensitive, the failure occurs by the nut section yielding. Okay. If you use that, that's too conservative because this will predict the failure to occur at a much higher level than any of these two. Okay. Now, in this region, this is based on 1 upon kT. Now, of course, KT, you will say 1 upon KT, KT is 3. But when you have a finite width correction factor, effectively the KT will keep on increasing. It's no more 3. In this is Y1 correction factor. For infinite plate, of course, KT will be 3. This will be 3, and the Y correction, this factor will be 1. But here we are considering, say, d by W, where diameter is increasing in comparison to the width of the panel. So this is what you see, KT is, that factor is changing. So Sn upon S0, which is the ratio of the notched strength and unnotched strength. Here you see, suppose a quasi-hysteropic, this will be 1 upon 3, which is 0.33. And that's what you have here. But because of the finite width correction rate, it will keep on dropping. So this is based on KT. What is this? This is based on the point stress criteria using 1 millimeter crack. This correct estimation, not crack, sorry, correct estimation 1.10. And when I, next slide, which I showed here, say, just to illustrate the point, you see here, this is test data for hole. And 2R by W is D by W, basically, diameter to width of the plate. And W is fixed over here. That means diameter is varying. Now, what you see from this test data, that this line is based on the point stress, and this line is based on KT. And what I said, so you see here, this data is here matching very well with the prediction using the point stress criteria. But when the hole size is large in this region, what you see, the predictions are matching well with the KT. So we take advantage of this criteria that when the hole is large, then you can predict the strength using the KT rather than using the point stress criteria. And this is what we normally would use. If the hole is like at 2 inches, don't have to worry about using the point stress criteria. You can just use KT. If you can determine the KT value for that layer, then 1 upon KT with configuration factor Y will give you the notched strength. Now, this is true for the hole only. For the crack, irrespective of the size of the crack, you have to always use point stress or Marlin approach. Does this provide you enough explanation for my reasoning of using that criteria, KT? Hello?
Yes, sir. Yeah.
Okay. And that is why I wrote the summary over here. The analysis, when you do, the hole size less than 40 millimeter, you can always use point stress. It doesn't matter. It will give you the same result. Because the equation for that will turn out to be same as than 1 upon KT for a very large hole. Okay, any other questions on so far this discussion? Okay, now I consider, so far we consider only the uniaxial loading. And in the real structure, life is not so simple as to just have the unidirectional loading and then determine the margin. It's far more complex. So generally you will have a multi-axial loading. What do you do with it in order to predict the strength? Well, there are 2 ways to do it. One is analytical method, but it is not so simple. because the equations are not in that closed form solution. The method was proposed by Garbo and Ogonowski, which is in this AFWL TR, this report, which I had sent earlier for bolted joints. And I mean, that is valid for filled hole and open hole compression, tension, that analysis. They use a complex variable technique in order to determine the stress distribution for multi-axial loading in a plate for the hole. And that's what you need. What you need from any analysis, you need the stress prediction near the hole boundary at the correct dimension. And then you use the point stress criteria. If I can predict the stress at any point over here, by whichever means you do, then at using the point stress criteria of Whitney-Newsmer, I can predict the strength for multi-axial loading. If this is not used, if you don't have the method available, then you can always use finite element method. So what you will use, the finite element method, again, you will use in order to determine the stress distribution near the proximity of the hole. And that means you need the stress at any point over here at characteristic dimension to determine the margins. Okay, so I have just solutions to stress field for holes in isotropic laminates discussed in this report. Those of you who are interested can access this report. This is even available from, if you go to the Google, and it's freely available. There are no simple analytical equations for the stress field, and the solution is not being presented here. I won't be able to write the equations because they are not so simple. But just providing the method. And so in order to determine the margins in such a case, for multi-axial loading, the procedure is you consider the characteristic dimension D0. So suppose you have determined the characteristic dimension for uniaxial loading. For simplicity, use the same characteristic dimension all across this, because the failure could occur here, 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 wherever the stress reaches the unknown strength value of the material under this multi-axial loading, because it will not occur right over here, maximum stress. It may occur anywhere. And that's why we consider, usually you will calculate using the equations or the finite element method, the stresses at various thetas, and then compare with your allowables at the characteristic dimension. Normally we use the strain criteria rather than the stress criteria, and at characteristic dimension for each layer in the fiber direction, determine the strain from either finite element method or Garbo-Ogonowski's method, that's a complex variable technique, and compared with allowable. That's the usual procedure. Now, suppose you want to use the stress constant approach, then rather than using the stress at characteristic dimension for a larger hole, then what you will do, you will, when you are doing the finite element modeling, you may have the beam elements along the whole boundary. So these could be beam elements. So you can pick up the strain beam strains for those beam elements right over at the edge of the hole, because the stress concentration method, when you're using, you pick up the stress or the strains right at the edge of the hole. And then compare with your allowable unnotched strength. Any question on this? I can't provide enough details of the procedure because it's not easy. I can just talk in general about it.
Sir,
Yeah.
excuse me, sir. For multi-axial loading also, you have to use the uniaxial, the characteristic distance approach derived from the uniaxial condition.
Well, that's what it is. It's not easy to determine for multi-axial loading the correct dimension calibration.
Okay.
And that's what you do. And what happens there, although this report, when you see here, they considered only the tension or compression, the correct dimension. But in general, we would consider the calibration or correct dimension for various types of loadings, like a tension, compression, the bending, open hole, filled hole, and then utilize that like we did for the bearing. Bearing also the same thing for bolted joints using correct dimension, where we determine the correct dimension for various types of loading. Of course, here you don't need the correct dimension for the for the bolt hole over there, which was there in bolt hole. Here, you will need like a filled hole tension, filled hole compression. Filled hole compression you can forget over here. Filled hole tension, open hole tension, and then you can use the bending also for the bending load. If there are no bending loads, then you don't have to worry about it. So only tension, compression, open hole, correct dimension could be good enough. So in summary, to your question, yes, it has to be determined based on the unit external loading.
Okay. Thank you.
Okay, so I have just written the procedure what I've already talked. Define the correct dimension, determine the fiber restraints. I won't read out because I've already told about it. Same thing for the crack. Again, now for the crack, of course, that analytical equation, like what I said, using Garbo-Ogonosky's complex variable technique, that is not available for the sharp cracks. Now, you have to use only the finite element method over here. There's no way you can determine the stress state analytically for multi-action loading. Procedure is same then, using the finite element method, and there's no stress constant approach here. You have to use correct dimension. So use the same procedure. You have determined the correct dimension, and at going around this one right over here along this, because high stresses could occur anywhere. So at various intervals, maybe 5 degrees interval you can use, or 2.5 degree, and determine at correct dimension the stress or stresses, compare with the liables to determine the margin. Okay, I won't read out here. Let's see. I think we have. We have enough time actually. I thought. Are there any other questions so far on this Marlin approach, point stress criteria? If not, I keep further. Now, So far we discussed about the notches in non-stiffened panels. But once again, in actual practice, every structure which will have the stiffeners, the spars, and ribs. And when you are dealing with such structures, the design condition always is there. Suppose these are the stiffeners, we have to design for the damage tolerance point of view, the condition is too big crack. So suppose you have a pitch equal to about 6 inches or 150 millimeters. So that means we have to analyze this panel for 300 millimeter crack. And not only that, you have to break the stiffener, assuming that central stiffener is broken. Suppose you have a spar. Again, I have not written a lot of cases, different cases. A spars, if you have to break the spar flange and partially the web for the crack. There are many scenarios. I won't go into the details of this. I thought this should give you some idea about the analysis. So what I have done here, although I can't go into the too much of details of these analysis because they are far more complex using the finite element method and the continuous damage modeling. I had sent a couple of references. And those of you who are interested in the damage tolerance for pursuing in a PhD level or further really might use those references. They're very useful. And I'll just talk briefly about those. Some of the methods over here. Not in detail, just briefly I'll touch on. Okay, so now in order to solve this, because these are practical problems for the aircraft structure, not a simple panel. They're all stiffened. Okay, so
Sir, here our
yes.
aim is to find the residual strength.
Yes, not the
And,
fatigue, by the way. We don't consider fatigue over here for these large cracks.
No, we are considering here the static strength.
Static only, residual strength requirement.
And sir, left side you have shown the compressive stress, right side tensile stress.
Well, this is compression, this is tension. Yes, compression also, the failure of a composite. It's not like metal, by the way. If we are dealing with composites, they are more critical in compression with the notch. One would assume a crack will close.
Yes.
And it doesn't fail. But unfortunately, compression has a lower strength than tension for the cracks.
But for metal, that is not that important.
Yes, metals is different.
Because crack will close under the compression.
Sure, I appreciate that.
Yes.
But in composites, it's not that simple.
Yes, because because that is different layers and that effect will be there. Yeah.
Usually we find the compression strength to be lower than tension strength. Of course, it depends on the material too. The issue with these materials is, say, what happens, I think I might have talked about during certification talk, that the improvement in the fibers and the matrix, you can, the compression strength of a laminate is the function of shear modulus, is controlled by the shear modulus of the matrix. Whereas the tension is controlled by the fiber strength. And there has been a lot of improvement in the fibers. So you have high strength fibers. Using those high strength fiber, tension strength has been increased compared to the old generation fiber materials. Today, suppose you have a T700 fiber, T700 or T800, compared to T300, the tensile strength has been increased by almost 50 to 60%. Unfortunately, the compressive strength doesn't increase by the fiber strength. Compression strength mainly depends upon the shear modulus capability of the matrix. And on one hand, we try to use, we say in order to improve the damage tolerance, impact damage tolerance of the composite, we use toughened material with higher toughness of the resins. Okay, that's perfectly fine. It does definitely improve the impact damage tolerance. Impact damage resistance, in fact, I would call rather than the tolerance. There is a difference between tolerance and that resistance. Because for the same energy level, suppose you have the impactor. If it's a brittle matrix, it will create larger damage than the ductile matrix or toughened matrix. Okay. Now, suppose you have the two damages which are same in toughened material and non-toughened material matrix. You test them in the compression. Suppose I have an open hole, okay, quarter-inch open hole in two laminates. One is using the same high-strength fiber basically, but one is using the lower toughened material, another using higher toughened material. Okay. And their toughness is higher, one is higher, one is lower. Unfortunately, what happens, the material which has a higher toughness has a lower modulus. Toughness increase reduces the shear modulus capability of the matrix. So as a result, the compressive strength with the open hole, like a quarter-inch hole, for the material which is brittle is higher than the compressive strength for the material which is ductile. So there's always dilemma in this when we are selecting the material. On one hand, we want to see better impact damage resistance, that is, creates a lesser damage. Another hand, we reduce the capability of the structure because open hole compression, we have to design with open compression, and unfortunately, open hole compression strength reduces. So we are always having these two contradictory factors when we are selecting the materials, because it's not a function of the fiber. Very small effect due to the fiber on the compression. Okay, having discussed that, let me just come back to this phenomena over here. So I'm showing this when you want to solve this problem, simple stiffened structure. A stiffener may be like a head type of structure, I section, the blade section, the J, or different other sections. And it becomes difficult to really determine the residual strength for those stiffened panel easily. It's not a simple solution. And when you want to predict the strength of these panels, because in aircraft structures, you may have a different regions with different type of stiffeners or spar thicknesses, the skin thicknesses, and everywhere you have to analyze the structure with a two-bay crack. Is it necessary for damage tolerance? So you can't keep on making the FEM model and keep on testing every type of panels to determine the reliables. It's a very difficult situation with the aircraft industry for these composite structures for determination of residual strength. Okay, now suppose we want to solve this problem that normally one is FEM method, which is reliable, of course, in such scenarios. Another is just, very elementary, using the empirical approach provided by Christopher Poe for metallic structures. I think I've put it in these two references. C.C. Poe, stress index factor for riveted and uniformly spaced stringers, and then effect of broken stringer, two reports. Christopher Poe from NASA Langley, and he did pioneering work on the fracture behavior, metal as well as composites. So I would be just providing that this method just to give you a feel, but nevertheless, it does not provide the actual answers for various types of stiffeners and various scenarios. Okay, so here, design requirement is that for a commercial transport aircraft, fuselage must be damage tolerant to penetration in the pressure shell up to approximately 12 inches. This is one criteria. And there's a strength limit to limit load. Another criteria is additionally the structure should be damage tolerant for a crack of 2 bay lengths with one frame or stiffener damaged. So residual strength corresponding to that 14 CFR 571D, which is for the larger damages. Get home load. Okay, so now in order to determine the residual strength of this, just trying to show some method. Residual strength analysis, empirical method based on CC pose, stiffened metallic structures, which again I will repeat, it's not very reliable. It's just to illustrate you, give you some feel. The reliable is FAM methods. There are a lot of FAM methods, and I've sent several reports to Prof. Dinesh on continuous damage modeling. They're very interesting. Or you can go to the NASA website. Most of the publications are coming from NASA website. There's a lot of data available from NASA web server. Okay, so this is from CPO. So now, in order to provide you a summary of using this method, I define mode 1 stress index factor. The crack tip is given by K1 unconfigured. I'm saying, okay, unconfigured means not a stiffened panel here, just a plain sheet with a crack of 2A. So why unconfig? I'm writing the configuration factor is why unconfigured factor. It depends upon the width of the panel divided by the this crack length. Sigma G unconfigured, which is a failure stress, is sigma G for unconfigured panel root pi A. Just fracture mechanics relation. Okay. I consider y unconfigured as 1 because I'm considering, okay, this is my infinite plate, although there's nothing infinity. We are considering, okay, the width of the plate we are choosing is much larger than the crack length. Okay, then we define, okay, stiffened structure. The crack, and we have a central stiffener here, is propagating on either side of this one. Again, let me tell you, we are not considering the fatigue. This is purely static analysis.
So this is metal or composite, sir?
It doesn't matter here for this method. We are considering composite, but this is the method I'm taking from metal.
Okay. Okay, sir.
The analysis which was done by Poe is purely for metal. But we are just using, okay, can we use those factors? That's what I'm trying. I'm just trying to show the method. And I keep on warning, this will not give you the exact result for composite stiffening unless you calibrate these factors. It is just to illustrate the method. So here, why I'm writing the configured panel, again, similar fracture mechanics relation. The only thing which is changing now, the configuration factor. Okay. We define a stiffening factor now, mu, which is ES-AS, which is stiffener area, cross-sectional area AS, and elastic modulus in this load direction ES, divided by ES-AS plus BT. B is the bay, T is the thickness, and E is the stiffness of this panel. Okay, so that's it. We call the stiffening factor. I've just juggled with the equation. I won't go into, you guys, just have written down solving this equation. So that means sigma strength of the configured panel is equal to sigma unconfigured upon Y configured panel. So what you need only the configuration factor for the stiffened structure, and sigma unconfigured can be calculated for the panel using a point stress criteria or Marlin approach. So to determine the failure stress for a stiffened panel, appropriate configuration factor Y configuration needs to be determined. That's it. Configuration factor is a function of the following parameter: stiffening ratio, A by ratio that is crack to stiffener spacing, stiffener type, and the material geometric parameters, bonded or bold fastened stiffeners, failed or intact stiffener, whether it's a failed or intact, stiffened bond strength, stiffener bond strength, and stiffener fastener pitch, so on. Okay, I've just copied some charts from this reference from Poe, just to illustrate here the method. Now, if you see this reference or the fracture mechanics book by Broik or any other book where they talk of the stiffened sheet for the metals, you can get the idea of this method. Now, what this is showing you, so this is a large panel with several stiffeners, and the stiffener spacing B, the crack length, say, semi-crack length is A. So the configuration factor, which is plotted from Poe, are depending upon the stiffening factor, because if the stiffening factor is very low, that means the configuration factors are pretty high, because mu equal to 0.05, that means stiffener is not very stiff. But as you reach higher value, the configuration factors keep on dropping. That Y configuration, depending upon as the crack is approaching near the stiffener, because if this stiffener is far away from this crack tip, the effect of this stiffener is negligible. That's what you see here. When A by B, when B is very large, that means stiffener is far away, the configuration factor is close to 1. But when the crack is growing and approaching the stiffener, the configuration factor will keep on dropping. That means the residual strength will keep on increasing as you approach the stiffener. So there are two things which are happening when the crack is increasing in length. One is, if you don't have the stiffener, the residual strength for larger crack will be lower. Okay? But that reduction is reduced as it approaches near the stiffener, because the stiffener tries to take the load away from the reduction by the crack. So the stiffening factor, the stiffener is providing you the higher capability of the panel. And this is what you see here when I wrote the equation, sigma configured is equal to sigma unconfigured. So that means the panel strength without the stiffener divided by Y config. So if the Y config reduces, that means the residual strength is increasing. Okay, so this is what it is. And this P by B, I just put up one chart where P is the fastener pitch and B is this D. So this fastener pitch. Now this will be different. If you have bonded panel, it could be different. And as I said, it is not, I'm not providing the exact method, but I was just illustrating that if you don't have anything available, probably approximately in the beginning to get some feel, you can use this method and test maybe a couple of coupons, to validate it. Now, there's another scenario where the central stiffener is broken, because that's the real case which you have to consider in your design. This case, no. We have to always break the stiffener. That means this case is not really useful to us in our aircraft industry. This is the one where, again, Poe had provided some charts, analyzed. Now, these charts are basically theoretical equations based on theory. He had developed the equations. Okay, now here this stiffener is broken. That's why I've shown like this one. And then again, same thing, the configuration factor. Now, if it's broken, that's why you are seeing now configuration factor to be more than 1. It's significantly reduced, because if the stiffener is broken, that means this is not capable of handling any load. So here the configuration factor with again, and I plotted here for mu equal to 0.5, the same thing, depending upon P by B, these factors are varying. So you can see again, as the crack approaches towards this stiffener, the configuration factor drops. And that means the crack tip, when it comes in close proximity to this one, the configuration factor is, because A by B 1, we are not interested in this region, because 2-way crack means only up to here the crack we want to study. And then our criteria normally in aircraft industry is this crack, when it's propagating, should divert, go as a delamination in this direction or divert this way. The stiffener should have the capability to divert the crack, and that is why one wants to study this damage growth model, the crack diversions, rather than crack penetrating through the stiffener or breaking the stiffener. That's a requirement to achieve the residual strength. Okay, won't go to details of this. And then you can determine after failure of the stiffener, what happens when the crack is propagating. That means the stiffener is loaded, picking the load. It doesn't provide the configuration reduction factor, because just like that, because when the crack is approaching here, that means more and more load is being shared by the stiffener. And that's what is being shown over here. The force in the stiffener basically increasing. Won't go into the details of it. Okay, so anyway, what I did, just as a typical example, I worked out to illustrate the method for a stiffener. What I did, say skin thickness, say 2.5 millimeter, skin E, some 45 GP. They're all hypothetical values. Just made up the values and picked up those characteristics from those charts. ES, just I assume, say 72 gigapascal for the stiffener modulus. B, that is pitch or the stiffeners, 150 millimeter. Initial correct length I consider 75, and then 112, 150. So E by B here, D1, correctest dimension I assume to be 1. So eta, Sn infinity, that is for just for the panel without the stiffener, is this is the strength you get. So that means for 75 millimeter is 0.162, and then it reduces to 0.115. In absolute terms, I didn't copy that value for, so S naught multiplied by this for unstiffened panel. I didn't copy that cell here, but don't worry about it. Anyway, so basically the strength of the panel without the stiffener would be this multiplied by this, all these values. And when stiffener's intact, that first chart which I showed, the stiffener, if you pick up the Y configuration factor, initially is 1 here, because there is no stiffener consideration we are considering. 0.162 here, 0.7, 0.67. So these values I have read from this one. This
Hello?
one, hello? Yes.
No, sir, please continue, sir.
Okay. So those configuration factor I picked up from this chart, which I have listed over here. Approximately again. So, and then using this one, these values, as you can see here, the notched strength, residual strength for the panel, 139, 118, 153. I've shown in the chart next sheet. And then when the central stiffener has failed, you can see for the same crack length, when the stiffener is intact, say for this crack length, when crack length is over here actually, A, 112 millimeters. This is say 118 is only almost half. Here 153, 91. So when the central stiffener breaks, it reduces the strength significantly. And so I have shown here the strengths. Okay. What you see here is strength, Sn, that is residual strength for the panel, stiffened and non-stiffened, with the stiffener broken or non-broken. So this one is central stiffener failed. You can see here for the small, this is small. As the crack is progressing further, the stiffener effectiveness is there, so it increases in strength. No stiffener breaking, you have the much higher residual strength, as we would expect. But if there is no stiffener, just for the panel, you see, and that's what you would expect. The residual strength without a stiffener now at this point is lower than with the stiffener. So this example was just to illustrate that one of the ways to determine the effect of the stiffeners is to use this method, which is very crude. Okay. Any questions on this? I think we just have 5 minutes to close this. So,
Sir,
yeah.
this work is published, sir. Any publication is available, sir, on this? Or suppose you want to refer this for some work.
Yeah, this is there. You see the reference here.
Okay.
Actually, in this presentation, which I sent today, these two references, Christopher Poe.
Okay.
And even if you, suppose these references I sent, actually, you can see in that drive, where Professor Dinesh might have put it.
Sir, we have to collect to Professor Dinesh, sir, na? These references.
I had sent this to Professor Dinesh, but if you don't have, then what you can do,
Pradeep,
go to
all of
NASA
these
web.
are available on the Teams itself. So this
Yeah.
Teams, if you look at the top tab of files, you can download any of the files, or you can go to the messages and download from the messages as well.
Or if you don't have access, go to the NASA website, NASA Technical Report Server.
Okay.
Just type CCPO, it will churn out at least a dozen reports by CCPO.
Okay,
But
sir.
on metallic stiffened structures, these are the only two reports by CCPO. So these charts which I have done here, of course, I copied from there. I meant just traced those figures and plotted over here. There are many, because different parameters are given in that. So you will find half a dozen to dozen charts with different parameters. It's useful, just look at it. Understand that. It's a very good method. Any other question? Anyone? Any question? No? No, there's nothing much here in this actually presentation now. And what I just wanted to, maybe tomorrow, maybe I'll spend just 5 minutes to highlight, because I'll not go into the details of this. I have written down some references over here for continuous damage modeling, and I've sent the references to Professor Dinesh. He would upload it into directory, which you can read, but they're FEM based, these methods, what you see here. And if somebody is doing, research, really they might just read them. Otherwise, there's no need for undergraduate students to go through this. But for information's sake, one can always go through. So maybe tomorrow I'll just discuss for 5 minutes what is there in one of the methods, and won't go into the details of this because it's FEM based. You can just look into the methods, those who are interested. Okay, if there are no questions today, we might.
Sir,
Yes.
Professor Dinesh, sir, how I can, Pradeep here, how I can download, sir, which link, sir?
So on Teams itself, the where you are attending this,
Okay.
if you go to the files, then you can download it.
Files,
There's a tab on top. Yeah. There's a tab on top. If you go to this particular team that we are on, there will be a tab called Team Files. So you can click on that and download it, or you can go to the chat box and download it. Can you see the chat box?
Not able to see.
Yeah, you can explore that even after this session is over. You can explore it and you can download.
Yeah,
The other students have also sent a message. You can see that how to do it. So you can check that.
I think I've sent almost dozens of reports now to Professor Dineshkumar.
Right.
It's
Tons of them.
overloaded, but they're all used for reference. Those who are interested,
Absolutely,
you know, it's not
No,
that
it's a database which will stay with us forever
Yes.
because it's very useful even for future students.
for the research students, they are useful.
Yeah.
Okay, any other questions tonight?
So for the audience sake, I'd like to remind you that the next session is tomorrow at 3 p.m. So please join us for that as well.
Yeah, maybe that may be the last one. Tomorrow, I think I would be able to finish this. Not
Right.
much remaining now. So I'll close tomorrow. I think it's good.
Right. Yeah.
Okay, so good evening from me for you people.
Good night, Dr. Garg.
Yeah.
And
Thank you very much.
Thank you, sir.
Thank you very much.